Hello everyone, welcome to the course on signal system. This is lecture 3 and in this lecture we will see some of the properties of Laplace transform. So before starting with the properties of Laplace transform, first let us revise what is ROC. We have seen. So ROC is known as the region of convergence. So region of convergence means it's the values of real part of S or sigma for which the Laplace transform of any signal xt or equivalently the Fourier transform of xt e raised to power minus sigma t converges. So we have seen what are the several properties of ROC. After the properties of ROC, we will start the properties of Laplace transform. So as we have the first property of the Laplace transform, which is the linearity. So the linearity means the linear combination of signals in time domain results in linear combination of the signals in S domain also. So that means if we have, let's say, a1 times of x1 plus a2 times of x2, so definitely the transform of as a whole will be a1 times of x1s plus a2 times of x2s. So accordingly, the region of convergence is basically the intersection of R1 and R2, whereas R1 is the ROC corresponding to x1, whereas R2 is the ROC corresponding to x2. So we can see that there is the intersection of both the ROCs, R1 and R2. Second property here is the time domain shifting. So time domain shifting means if we have the time shift in the input signal, let's say if we have x of t minus t naught, or let's say we have x of t plus t naught. So as per the analysis equation, we can see that there is an exponential part which is e raised to power minus s t naught multiplied by x of s. So if it is x of t plus t naught, so definitely here the exponential we are having a positive quantity e raised to power plus s t naught multiplied by x of s. So we can see here that clearly that due to this exponential factor added with the Laplace transform x of s, we can see that there is no change in the location of poles. So if there is no change in the location of poles, so whatever is the ROC of xs, the ROC of x of t minus t naught or t plus t naught will be exactly same. Next property, third property, which is the Laplace domain shifting, means the shifting in S domain. So if we have a shifting in S domain, so x of s minus s naught, so as per the equation, the inverse transform will be e raised to power plus s naught t multiplied by xt. Or if we have the positive sign over here, so naturally we'll be having negative in the exponential side. So now we can clearly see that if we are having x of s minus s naught, so each and every pole will be having an additional component of s naught. So what we can say that the new ROC will be existing ROC plus real part of s naught. S naught may be a complex quantity. Next is the scaling property basically. Either we can say time domain or Laplace domain scaling. So if we have, let's say, x of at, so a similar kind of property we have already seen in case of Fourier transform. So if you remember that x of at, the transform was 1 by mod of a x of omega by a. So a similar kind of property we can derive with the help of Laplace transform also, and we can see that we have 1 by mod of a x of s by a. So we can see that if we have, so for example, 1 by s plus 4, and if we are performing a scaling in the signals, accordingly we have to replace s by a. So instead of s, we can put s by a. So accordingly the new pole will be at minus 4a. So the new ROC has to be, the ROC will be multiplied by that particular factor a. Next is the conjugation property. So x star of t, we can say that we are having x star x conjugate of s conjugate. Again the ROC remains same. Now time domain convolution. So as you people are already aware that the convolution in one domain basically results in the multiplication in another domain. So if we have the convolution of two sequences or the two signals x1t and x2t, so we can see that we have a multiplication x1s multiplied by x2s. So if let's say two polynomials or two fractional quantities, let's say they are multiplied, so accordingly the ROC, new ROC has to be the intersection. It is basically the intersection of R1 and R2. Next is the time domain differentiation. So if we can see that d by dt of some xt, so accordingly we have seen a similar kind of property in Fourier transform also, that the Laplace transform will be multiplied by a factor of s. So we can say that again we have the ROC, at least the existing ROC R we must have. Now Laplace domain differentiation. So as we have differentiation in time domain, a similar kind of result we have in the s domain also. So d by ds of xs, it will result in a signal which is minus t times of xt, and again we can see that there is no change in the location of poles if we are applying this Laplace domain differentiation. And finally we have the time domain integration. So time domain integration, we can see that we have x of s by s, means we are adding a new pole at s equal to 0. So if we are adding a new pole, so definitely we can see that the new ROC has to be the intersection of the previous one along with the real part of s greater than 0. So these are the properties, very important properties of Laplace transform, and we have seen that what is the effect of applying these properties on the ROC, which is quite important. So after this we'll try to implement these properties with the help of these numericals. So find the Laplace transform of xt equal to u of t minus 1. So as we are aware that we have to solve these type of problems with the help of properties. So how can we start the property? We have to apply the properties from right to left. Right to left. So right to left, we can see that there is some shifting in the signal. The signal was ut, but we have u of t minus 1. So if ut we have, so the transform will be 1 by s, and accordingly the ROC has to be real part of s greater than 0. But if we use the last property which we have seen, x of t minus t naught, so there has to be a factor which is e raised to power s t naught. So u of t minus 1, we have e raised to power minus s t naught multiplied by the transform of ut. So the transform of ut is 1 by s. So the final result is x of s equals to e raised to power minus s divided by s for all real part of s greater than 0. So we can say that the ROC of the new signal, which is u of t minus 1, and ut, which was our xt, the ROC was same. So we have basically proved that the second property, time domain shifting, there is no change in the new ROC. So after this we have the second example, that we have to utilize the properties of Laplace transform and the transform pair, and we need to calculate the Laplace transform of e raised to power 5t multiplied by e raised to power minus mod of t. So first of all, before starting with this, we need to understand that if e raised to power minus mod of t, it's a both-sided signal. So if the signal is a both-sided, so definitely the ROC has to be between two poles but does not contain any pole. So that's why the ROC is between minus 1 and 1. We can clearly see that. We have this minus 1 over here and we have this plus 1 over here. And the ROC is a region which is lying between these two poles but does not contain any pole. So this is the ROC. So it is clearly mentioned here. And also we must be aware that since it is a both-sided signal, so ROC is between two poles. Now we have to utilize this to calculate the transform of e raised to power 5t multiplied by e raised to power minus mod of t. So this is e raised to power s naught t multiplied by xt. So if we see, if we can recognize what property we are going to use here is, it's a shifting in S domain. So shifting in S domain, there has to be x of S minus of S naught. So in x of S, wherever we have S, it is going to be replaced by S minus 5. So we can see here we have the solution. So x of t, we have the transform which is called as x of S, like this, and we have some new signal which is x1t. We can write down that x1s is whatever we have x of S, we are going to shift in S domain. So we have to put S minus 5, and we can further solve this, and after solving this we can see that we have the poles, we have the new location of poles which is minus 4, which is plus 4 and plus 6. So plus 4 and plus 6, if we can see, this is plus 4 plus 6. So the region is basically real part of S greater than 4 and naturally it is less than 6. So the region is between two poles like this. This is the ROC. So if we can recognize that previously we have the ROC was real part of S greater than minus 1 but less than 1, and now we have real part of S greater than 4 and less than 6. So what is the relationship? Means we have added 5 which is S naught, real part of 5 which is also 5. So we are adding 5 both the sides. So accordingly we have the new ROC will be minus 1 plus 5 and 1 plus 5. So that has to be between 4 and 6. So this is the second type of problem we have seen. Now using only the properties of Laplace transform and the transform pair, find the Laplace transform of e raised to the power minus mod 3t. So if we can see that previously we have a signal, but the new signal is having a factor of 3. So 3t means we have to utilize a scaling property. So scaling property basically says that if we have x of at, so the Laplace transform of this signal will be 1 by mod of a x of s by a, whereas the new ROC will be basically a multiplied by the previous ROC which was mentioned, let's say. So first of all we'll be having the transform, it is already given, and we can have the transform of e raised to the power minus mod of 3t with the help of this particular property. So wherever we have s, it will be replaced by s by 3, and also we have 1 by mod of 3. So 1 by mod of 3 to divide by 1 minus s by 3 ka whole square, and we can see that the entire ROC is basically multiplied by a factor of 3. So it will be minus 3 to plus 3. So finally what we have is, after solving this x of s, we are getting minus 6 whole divided by s plus 3 multiplied by s minus 3. So the new ROC, if we want to plot, so it is minus 3 which will be lying somewhere, and which is plus 3 like this, and the ROC is definitely between the poles, between two poles like this. This is region of convergence. So we can clearly see that whatever we have the previous ROC, the new ROC is multiplied by a factor of a. And what was a? If we can see, a was 3. So the new ROC is a multiplied by r. Next we have, again we have to utilize the properties of Laplace transform to find out the the convolution basically. So x equals to x1 t or convolution with x of t. So as you people are already aware that convolution in time domain is basically the multiplication in s domain. So first of all, how we are going to calculate the transform of x1t? If we can see, it can be written as e raised to power plus 3jt minus of e raised to power minus 3jt whole divided by 2j. We can write down, and it is multiplied by ut. This is x1t. So how we can calculate x of s? We can calculate x of s by applying the property. So property means first of all we will be calculating the transform for ut. We are already aware it is 1 by s. After that, this is shifting in s domain. So we will be having two terms. One is 1 by s minus of 3j, and the second term will be 1 by s plus 3j. So this is nothing but x1 of s. Similarly, we can calculate x2 of s. So t times of xt. T times of xt, it is nothing but, if we can remember, t times of xt, the Laplace transform will be minus of d by ds of x of s. So we are going to utilize this particular property and we'll be calculating the transform for x of x2t. So basically we have utilized directly that if we have sine of at u of t, so the Laplace transform will be a divided by s square plus a square. A similar kind of result we can have for cos of at u of t. The Laplace transform will be s divided by s square plus a square. So we have the first transform, which is x1 of s, and this is s square plus 9. So if we can find out the roots, so this will be s equal to plus minus 3j. So plus minus 3j, if we'll talk about what are the real part of s. So the real part of s is definitely 0. So real part of s greater than 0 is the ROC for sine 3t ut. Now we need to calculate the transform for x2t. So x2t was t times of ut. We utilize the property which is minus d by ds of x of s. So we have to basically differentiate 1 by s. We are getting 1 by s square for all real part of s greater than 0. Now we have the property that convolution in time domain is nothing but the multiplication of the transforms in s domain. So we have 3 divided by s square plus 9 first factor, and we have 1 by s square. And for all both x1s and x2s both have the ROC, which is real part of s greater than 0. So by simplifying this above expression, we can say that our final transform x of s is 3 divided by s square multiplied by s square plus 9 for all real part of s greater than 0. Means if you want to show what is the region of convergence for this convolved signals, so ROC is like this, and we can see the poles are at plus 3j and minus 3j. But we must remember that the ROC depends only on the real part of S. That's why the real part of both plus 3j and minus 3j is 0, and the ROC is right to the rightmost pole like this. So this is the ROC of sine 3t ut convolved with t multiplied by ut. So we can see that these are the basic problems where we can utilize the properties of Laplace transform. So by the help of Laplace transform property, we can basically simplify those questions. Now, using only the properties of Laplace transform, again, find out the Laplace transform of t e raised to power 2t multiplied by ut. So first of all, before starting with this, we need to check what all properties we can apply here. So we are already aware that e raised to power minus 2t ut, the transform was 1 by s plus 2, whereas the real part of s greater than minus 2 is a ROC for it. Now t multiplied by xt. If you remember, t multiplied by xt, naturally the transform will be minus of d by ds of x of s. So we can see that we are having d by minus of d by ds of x of s, whatever we have the previous one, 1 by s plus 2. So by differentiating with respect to s, we can achieve that we have x of s equals to 1 by s plus 2 whole square. Now we can see that 1 by s plus 2 whole square means there is no change in the location of poles. So we have basically the repeated poles at s equals to minus 2. Like this. So the ROC is basically greater than minus 2 because we are already aware that xt is nothing but a right-sided signal. So definitely the ROC is right to the rightmost pole but does not contain any pole. So these are the properties which we have used in this particular numerical. Now our last question based on this, we have to find out the Laplace transform of the signal, which is t e raised to power minus 3 mod t. So as we are aware, it can be written as e raised t multiplied by e raised to power 3t u of minus t plus t e raised to power minus 3t u of t. So basically individually we can calculate the transform for these two, and we can use the linearity property which says that xt equals to, let's say, some a1 times of x1 plus a2 times of x2. So naturally the transform will be basically the addition of both x1s plus x2s. So by solving this, we'll solve this further, or individually we can see what are the corresponding ROCs. So this part is corresponding to the left-sided signal. So definitely the real part of s is less than 3, whereas from this part, this is corresponding to a right-sided signal. So definitely the ROC has to be right-sided. So real part of s greater than minus 3. So what we have now, since in linearity we have seen that we must be having a intersection of both the ROCs. So finally what we have x of s equals to minus 12 by s plus 3 whole square, s minus 3 whole square. And the ROC is between minus 3 and plus 3. This is the region of convergence. So these are the properties by which we can simplify the numericals corresponding to the Laplace transform. So one final topic we are going to see, these are some important theorems, initial and final value theorems. So initial and final value theorem, these theorems are helpful in deciding or calculating the initial value, means the value of the signal. We are talking about x of t. So if we are talking about initial, means at t equal to 0. And the final value theorem means the value of x of t at t equals to infinite. So the theorems which are helpful in deciding, in calculating the initial and final value of any given signal are known as initial value theorem and final value theorem. So let's say if we have a function x and the Laplace transform is capital X. So if x is causal and contains no impulse of higher order singularities at the origin, So we can say that x of 0 equal to limit s approaches infinity x of s. So if we have the Laplace transform x of s and we want to calculate that what is the final value of the signal, what is the initial value of the signal. So t approaches 0 is nothing but s approaches towards infinity s multiplied by x of s, where we can see that x of 0 plus denotes the limit of xt as t approaches 0. Now we have the final value theorem. Again, this final value theorem says that limit t approaches infinity xt can be written as limit s approaches 0 s multiplied by x of s. Now there are some conditions which are added with the final value theorem. So both initial and final value theorem are applicable for a stable system. Both are for stable. Or we can say, before starting with the stability, we must say that both the theorems are applicable for the causal systems. And we can say that the final value theorem is meaningful if the poles of x of s lies in left hand side of S plane. So final value theorem is meaningful if the poles of x of s lies in left hand side of S plane. What does it signify? It signifies that if the poles are lying in the left hand side of S plane, it shows that the system is stable. Means the final value theorem is applicable for the stable LTI systems. So these are the important theorems, initial and final value theorems. In the next lecture, we'll see some of the numericals based on these. These are the references. Thank you.